Okay, this is your atmosphere and air pollution video. This is chapter 18 in your Miller PDF textbook. And one of the slides I want to talk about is regions of the Earth's atmosphere. This includes the ozone layer. And if you look, we've segregated it into lower atmosphere, which includes the troposphere and the stratosphere, and the upper atmosphere, which includes the mesosphere and the thermosphere. And the pauses are the regions between those. Of course, it's not a discrete separation. It'd be a kind of transition, but you've got your tropopause and stratopause, and I'm going to focus on these two lower regions, troposphere and stratosphere. That's where all of our pollution is. That's where all of our weather is. That's where all of our planes fly. So the top two regions I'm not going to spend much time on. If you look at this, we've got temperature down here and altitude. We got two scales of temperature, and then on the left we've got altitude in kilometers. On the right you have altitude in miles. And let's focus on this blue line, which is the change in temperature as a function of altitude. As we notice, as you move away from the Earth, the temperature decreases. The reason is this: the Earth is absorbing a lot of the energy coming from the sun, and therefore it warms up. It then readmits that, and that has a warming effect. So as you move away from the Earth, it's colder. You can't think about moving closer to the sun because that's kind of insignificant. The distance is minuscule compared to the total distance to the sun, so it's insignificant. So the temperature decreases as you move away from the Earth. The question is then, why then all of a sudden does it start increasing here? So what you have to picture now is we have a sun that's emitting a lot of electromagnetic radiation. And let's say we've got a bunch coming through here. Well, then it starts to get filtered out as it goes through these different regions. And then ultimately, a bunch is filtered out and only some of it gets through. So what's happening here is the ozone molecules, which is O3, absorb ultraviolet light. And when they do this, they become energized. So a molecule absorbs and becomes energized. And that is what you're measuring. When you measure temperature, you're measuring the kinetic energy of the molecules. So in order to measure temperature, you're going to hold a thermometer, right? The molecules have to collide with that thermometer. And the energy of which they collide with that thermometer is what causes the mercury in the thermometer, or whatever liquid you're using, to rise. So the reason you see an increase in temperature is we have a lot of absorption of this UV light, which causes these energetic molecules, and then you see an increase in temperature in that region. Then it starts to decrease again as you get further from the Earth. Up here it's a little bit odd. I'm not as concerned that you understand this, but let me just say that temperature can't be really measured up there. Air is too thin. So if you hold a thermometer there just won't be enough collisions with the thermometer to measure temperature. So what those temperatures are calculated temperatures, okay? So that's generally how the temperature changes through the atmosphere. Now I want to talk about something else that's not on here, and that's pressure. How would pressure change if we were to graph pressure on the x-axis versus altitude? And what is pressure? Well, it's force per unit area. Whoops, that's supposed to be a line like that. So it's the force of air sitting on top of the Earth. That's the pressure. So as you get higher up, the pressure should be less, and that's what you see. You see something like this. Pressure decreases as you go up in altitude, if this is increasing pressure in this direction. And you know this from various things, but for instance, Mile High Stadium, the air is said to be thinner there. Less pressure, less column of air sitting on you, tougher to breathe because the pressure is what drives the air into your lungs. So you say some athletes, that aren't trained up in that altitude have trouble breathing, that type of thing. So pressure would look something like this if you were measuring it as a function of altitude. So going further with pressure, take a look at this now. So what we're going to do is we're going to take a tube of mercury, and we're going to fill it to the very top with mercury. Okay? Now we're going to turn it over without letting any air into it and put it into a trough of mercury. So what happens is the mercury will settle under the force of gravity, and this right here will be a vacuum, because you didn't let any air in. And it's not a true vacuum, but the idea is now this mercury can rise and drop because there's not air blocking it. If that was filled with air, it wouldn't be able to rise. So now what's happening is the pressure of the air is pushing down on the mercury and forcing it up the column. The level to which it rises is directly related to the force of the air pushing on it, but also gravity, two opposite opposing forces, right? Gravity wants it to fall back down. So it stops when those two forces are equal. And at sea level, that's going to rise about 760 millimeters. Oops, sorry. And you know what millimeters are? 760 millimeters is 76 centimeters. And 76 centimeters, well, that's a quarter of a yardstick, because there's 100 centimeters in a meter. A quarter of a meter stick, sorry. But a meter's roughly a yard. So you can think about it as a quarter of a yardstick. So it's not too high. And the reason we use mercury is because the density is high. Grams, 13.6 grams per milliliter, where water's about 1 gram. We should learn that in lab. So you can make a barometer, it's called a barometer, and measure pressure out of water, but it would rise like something like 30-something feet, 13.6 times as high as mercury. So we use mercury for its density because it won't rise so high. But really, it's the balance of those two forces. So if I took this up to Mile High Stadium now, I believe the pressure there is something like 0.83 atmospheres. So it's about 83% of what it is at sea level. Murfreesboro's probably pretty close to sea level. It's a pretty low area, slightly above sea level. So the barometer would only rise up to maybe here if you took it to Mile High Stadium. So that's really an explanation of pressure and how it works. This is just showing you those regions of the atmosphere. Got some characteristics here to look at. You can spend some time looking at that. I don't really need to say much about that. This next slide also shows some characteristics of gases in the troposphere. And over time, this number has increased. As I've taught these classes. We're up around 400 parts per million. Percent volume is given, and also parts per million. We've learned about parts per million a little bit in lab, I believe. ppm. So there's only one significant figure here, and that's why it's 0.04. Even when this table was created, which was several years old. But back then it was about 360 parts per million. When 10 years ago, 10, 20 years ago, it was 360, 450 parts per million. Now it's up about 400 parts per million in present-day concentrations. And you look at nitrogen's about 78% of the atmosphere, and oxygen's 21%. That represents 99% of all your atmospheric gases. A lot of people don't realize argon's the next most abundant gas in the atmosphere. And then, of course, you have a host of other gases. And this is obviously not showing you water. Water vapor varies. This is for dry air. Then characteristics of the stratosphere. That's where your ozone naturally occurs. It's roughly around 15 to 35 kilometers, and it filters out ultraviolet radiation. Now, in the air pollution, this first reaction here is really important. This is taking place anytime you burn fuel for energy. So it's taking place in your car. It's taking place when we burn coal. Because the atmosphere is mostly nitrogen, remember, and there's tons of oxygen there too. This reaction does not happen at regular temperatures. So if you just go outside today, and you're not going to have nitrogen reacting with oxygen to form nitric oxide. But when there's temperature present, high temperatures, like in your combustion engine, then you're forming nitric oxide. This is one of the key precursors to photochemical smog and a key pollutant. Ultimately, it goes on to form nitrogen dioxide, which is a lot of that brown haze you see over cities, and ultimately nitric acid, one of the components of acid rain. But all three of these are basically air pollutants. But it's important to realize that it only happens at high temperature. Now, one of the things we have problems with air pollution is when we get temperature inversions. So these are normal conditions on the left, and pollutants can easily escape, as you can see. Now remember, warm air will be less dense. Why? It's more spread out. Just think about what happens in the summer. The wood of your doors expands and becomes tighter, right? air expands, it becomes less dense. Well, occasionally what happens is it's due to different geographical patterns. Here we got a valley. You can have currents from oceans, things like that. But you wind up with um, warm air overlying cool air. And as a result, um, the cool air is more dense, so it doesn't tend to escape and gets trapped, and now your pollutants are trapped here. So the idea is we've kind of got this warm air that's slid in and overlies some cooler air. And air pollutants get trapped, and that creates a lot of problems. Photochemical smog is a big topic, something your book talks about, you need to become familiar with. It's very different than industrial smog, which came from burning coal, basically, which was basically a combination of smoke and fog. But this is really these brown hazes I've talked to you about. And here it is. Here's the car exhaust reaction, the NO that forms, and then on to NO2. And then with sunlight present, we get to form this again, so it can cycle back around. You also form singlet oxygen, which causes formation of ozone, which is fine in the stratosphere. It protects us, but in the troposphere, it's a pollutant. And you can see this can just keep cycling around because we're forming these, and there's other reactions that actually reform oxygen. So you get these completely cycling around and keep forming over and over. This is photochemical smog. And there's three things you need to have. You need to have those nitrogen oxides, really four things if you count this as two, and hydrocarbons, then your sunlight and temperatures. And the hydrocarbons come from unburnt fuel. And what happens ultimately is you get all these different compounds forming, things like VOCs and aldehydes and PAN, which is peroxyacetyl nitrate. And I gave you some references in your book to look at this and read at this, and you have some other figures in your slides. And here's one right here. There's some of your hydrocarbons. There's your aldehydes. There's your peroxyacetyl nitrate compounds. This becomes basically like a photochemical soup of noxious compounds. That's why it's not good to jog at rush hour times. You're breathing a lot of this stuff. Ultimately, one of the things that can come about too is acid rain. So I talked about some basics of what acids are within your slides, but I'm going to talk a little bit more about it here. Acids are what we call proton donors. So you look right here. This is nitric acid. It's going to donate this right here to water and form H3O positive. That is what you're measuring when you're measuring acid. And it's impossible to tell by looking at something whether that hydrogen is going to come off. It doesn't always come off. You have things like your alcohols. That hydrogen doesn't come off. These hydrogens don't come off at all. So there's no way for you to know that. You don't have that chemistry knowledge. So let me ask you, just get familiar with the idea that an acid does donate that hydrogen. And because a hydrogen ion is just a proton, because this is the main isotope of hydrogen, which means one proton and 0 neutrons. So if it loses its one electron, the only thing left is the proton. And that's why we call it a proton donor. Well, the complement of that, if you will, if you take water and break it down to its two components, you got the proton and the hydroxide, what's left over. That's what makes something a base. So it's kind of like the opposite. The two of them come together, they can neutralize and form water. So this is kind of what you're measuring. This is always what you're measuring. This is the complement of that. And lots of people just write this, but it really is H3O positive. You can't just have a proton floating around in solution, so it combines with water. So as a result, rainwater is naturally acidic because of carbon dioxide. You can't tell by looking at carbon dioxide because it doesn't have a hydrogen there, but it reacts with water to form carbonic acid. Both of these hydrogens can actually come off. So natural rain has a pH of 5.6 before humans ever walked the planet. To be considered acid rain, even though 5.7 is an acid, to be considered acid rain is referred to polluted rainwater. That's really the way the term is used. Natural rainwater is acidic, but acid rain has to be less than 5.6. So you see your pH scale here, and ultimately, like I said to you, what you are indeed measuring is that hydronium ion concentration. You can see 10 to the minus 1 means a pH of 1 because pH is actually equal to the negative log of that hydronium ion concentration. If you remember your rule of logs, the log of 10 to the 3 is equal to 3 because it's base 10. So it's like saying 10 to what power equals 10 to the third? It's 3. So if you have a negative log and you're doing the negative log of 10 to the minus 3, it becomes 3. So that would be a pH of 3 right there. So that's really what you're measuring. And you can get pH ranges outside of this, but this is the normal pH scale. And you see battery acid solutions way down here, oven cleaners way up here. Here's pure natural water if you had nothing dissolved in it. Blood is very close to neutral, but you can see different species that are acidic and then different species, substances, I should say, that are basic. And that's your pH scale. So here's a map of acid rain. And the reason the Northeast is inundated is not because they pollute more. It's because we burn most of our coal in this region of the country. And because of the jet stream, this is where it travels. And eventually it precipitates out. And that's why you see a lot of lakes and regions in that part of our country experiencing acid rain. And I think I mentioned on one of my slides the main components of acid rain. You can see that sulfuric acid, nitric acid, and hydrochloric acid are the three main components of acid rain. I think I give you the percentages. Some of the effects of acid rain, it can actually dissolve materials, acids. So if you have a lot of like structures that are monuments and sculptures, like in Italy, everything outside is all these incredible sculptures. You've got buildings that are important to you. They will actually dissolve slowly over time. But that's the least of the problems. It does impact lakes. Fish are impacted both by the low pH, but also by the leaching of things like heavy metals from the soil. So things like lead can be leached out of the soil. This would be held in the soil, but hydrogen ions come along and replace that, and this becomes now available and can be toxic. It affects the plant leaves. I think it affects their ability to exchange gases. Somehow it messes with the stomata, which are the little cells that exchange gas. Aluminum's another metal that gets leached out. It can affect roots of plants and microorganisms. And then good metals that are needed by the plants get leached away, things like calcium. Human health, it's more of a breathing issue. You get aerosols in the air that can irritate lungs and respiratory tissues. That's the only real concern there. We're not going to dissolve, that's for sure. So some of the successes and some of the things we've done to control our air pollution, these are two ways in which you can actually filter particles. So this one on the right is really just an elaborate vacuum cleaner. Bags that actually filter out particles. Because one of the big problems with air pollution, and you saw that in the slides, is particulate matter. These are particles that get trapped in your lungs and cause problems. Well, these bags will actually filter that out. So you could put this on like a smokestack. This one's just an elaborate way of doing that using charge, causing the particles to be charged and then attract to a charged surface. They can also be removed that way. Catalytic converters. All of our cars have catalytic converters now. And these contain three precious metals: rhodium, platinum, and palladium. And what they basically do is they, in a very short amount of time, just think about how long the exhaust moves through your catalytic converter and then goes out your exhaust pipe. We're talking about a couple seconds here. What you're looking at basically is pollutants like nitric oxide and carbon monoxide, which I talk about in the slides and your book talks about, and unburned hydrocarbons can now be converted with the presence of these catalysts in two separate reactions. Catalysts just speed up reactions. Remember, we said this. Without being consumed, I introduced that idea in the toxicology slides. And they converts them back to the benign stuff that's not pollutants. Now, CO2, we have issues with climate change, and that we'll talk about in another chapter, but otherwise it's not a toxic pollutant. It is a pollutant, but for different reasons. So these catalysts basically just speed up the reaction. And in your in your car, you basically have this honeycomb-like material. It just basically provides a lot of surface area for the pollutants to come together on that surface, and then they can go and form N2 and O2. So it just speeds up reactions that would normally be too slow to take place. Now you can also do things with stationary sources, not just transportation. Sulfur can be removed from the coal before you burn it. You can also burn it on a bed of material that absorbs the sulfur as it burns. And you can also remove the sulfur dioxide, which comes from the burning of the coal, afterwards in kind of a scrubbing type process. With that, that concludes my introductory video. So make sure you read the chapter and listen to the video and look at your slides.